In previous videos, we've talked about solving different types of equations. So for instance, we've talked about linear equations and solving those things, where we have the highest power of x being just x to the 1. And for this, we would get the x's onto one side of the equation and get everything else to the other side, and then solve for x. For quadratic equations, the way we solve this is get everything over to one side of the equation, so it equals 0. So in other words, subtract 2, and then I'm going to rearrange this equation. And then now what we can do is we can try to factor this thing to solve. So those two types of equations are by far the most common. They're the simplest kind of in form to solve, but there are other types of equations that we like to solve. And kind of following along this line of linear then quadratic, the next step up would be polynomial equations. And polynomial equations are just those that have higher powers of x other than x squared. Not all of these can we do we have methods to solve. We might need to like simplify it using higher techniques if it's a higher power, and that's kind of beyond the scope of this video. But for these ones, we have a cubed. That's the highest power of x is x cubed, and then x to the 4th. And these ones just happen to be ones that we should be able to solve using some strategies. So for this cubed one, I'm going to get everything over to one side. I'm going to subtract the 9x and add the 27. Getting over to one side, and that'll give us 4x cubed minus 12x squared minus 9x plus 27, and that equals 0. Now, if it's a cubic like this, we can try factoring by grouping. So I'm going to look at these first two and then these next two and ask what can I take out of them. So from the red, I can take out a 4x squared. That gives me x minus 3, I believe that's true. Yep. And from the blue, I'm going to take out a negative because we have a negative here. So this becomes a negative, and then 3, and that's the most I can take out, I believe. That's going to give me an x minus 9 here. So I didn't take out enough. This was actually going to be 3x 9. So actually I can take out a 9 in front of this. And that ends up giving me x minus 3 here. And the reason why I kind of hesitated there is because I knew that these two things need to be the same to continue. And so I was able to check my work and then put the right numbers in there. Now the green is the same, so I can write down that. We get x minus 3. Then on the outside, we have 4x squared minus 9. And this equals 0. Now we're not done yet because this 4x squared minus 9, that is a difference of two squares. In fact, it's going to be 2x squared and 3 squared. So I can factor this thing further. The x minus 3 is the same thing. I'm not touching that at all. But the difference of two squares becomes the first thing minus the second thing, the first thing plus the second thing. That's the method of factoring difference of squares. It's just going to be whatever this thing is, and then whatever that thing is, and then the plus version and the minus version. Whichever one whichever one can go first. It doesn't matter which one, but as long as you have both of them, you're good to go. Now I can solve this by setting each one of these things individually equal to 0. If any one of them is equal to 0, then the whole thing becomes 0 because they're all multiplying. So let's do that. We get x minus 3 equals 0. This means that x equals 3. 2x minus 3 equals 0. Well, you can add 3 and divide by 2. That gives you x equal to 3/2. And then 2x plus 3 equals 0. This implies x equals negative 3/2. Very similar process. So we actually have three answers. We have 3, 3/2, and negative 3/2. And that will directly come from the fact that we have a power of 3. that power will typically always give you the answer, the number of answers you should expect. Sometimes you will have less than that. You will never have more than that. For this next one, we're going to solve it very similarly. I'm going to get it all over to one side. So 3x to the fourth minus 81x. Now I can take out a 3x from both of them. It's going to be x cubed minus 27. And this is a difference of two cubes. We have x being cubed, and we have 3 being cubed, not squared, cubed. And the formula for that, if you don't remember, is the first minus the second. And then we have the first thing squared plus the first times the second, so 3 times x. And then the last thing squared, so 3 squared is 9. We're going to add that. That equals 0. This one will not be able to factor any further, and therefore we will not get an answer from it that's that we'll know how to do. Everything here is going to be positive, I believe. So it can't equal 0. But these two things can. So we have 3x equals 0 when x equals 0. And x minus 3 equals 0 implies that x equals 3. So we have two solutions here. And you can see that it is less than 4. This term should add in two complex solutions, but we're not concerned about that. I can actually show you that real quick by using the AC method. So we have 1x squared plus 3x plus 9. So a equals 1, b equals 3, and c equals 9. And using the quadratic formula, we get x equals negative b plus or minus b squared, which is b squared is 9, minus 4 times a. 4 times a is 4, times 9 is 36, all over twice a. So 2 times 1, or 2 times 1 is 2. And you can see that inside of the radical, we have a negative. This part gives us the complex because there's a negative underneath the radical. And therefore we have two complex solutions, the plus and the minus version of this. So we're not concerned about that right now. We're only concerned about real solutions. And that's what we have here with the x equals 0 and x equal to 3. In addition to polynomial equations, we also have radical equations. And radicals are different than polynomials because polynomials will never have a fractional power like the radicals bring in. The square root is a power of 1/2. Polynomials never have anything other than whole numbers for the power. So 0, 1, 2, 3, 4, 5. So this is distinctly different than the polynomial equations, even the linear and quadratic. But we can still solve these things. And the method for solving them really is to get the radical by itself and then take the power. So for both of these, we have square roots. And so we're going to take a squared power. If it was a cube root, we would take a cube power, and so on. For this first one, I'm just going to get the square root of x plus 11 by itself. So I'm going to add that to the other side of the equation and then subtract 1. What that'll do is it'll give me x minus 1 equals the square root of x plus 11. Now I can get rid of the radical. I can do that by squaring. Now, what's important to note here is that you square everything on both sides of the equations. You may, if you had something like 1, let's do something like this, x over 2 equals x plus 1. You could here multiply everything by 2. And that will work out perfectly fine. The reason why it can do that is because what you're actually doing here is multiplying everything by 2. But multiplication is distributive. And so it essentially is the same thing as multiplying everything by 2. This, however, a squaring, this is not distributive over addition. It is over multiplication. So if I had something like 2x and then I squared it, this is the same thing as 2 squared times x squared. It does distribute over multiplication. It does not distribute over addition. Do not make the mistake of saying that this x minus 1 is the same thing as x squared minus 1 squared. They are in fact never true, except for one very, very special case, and that's very rare. So don't worry about that. Never assume that this is true. Always make sure you square everything and expand it, because x minus 1 squared is the same thing as x minus 1 times x minus 1. The square root and the square cancel, giving us just x plus 11. And this is now a quadratic equation. So by squaring it, we've changed the problem from radical to quadratic, and we know how to solve those. We just expand everything out, get it all over to one side, factor, and solve. So doing the FOIL method on the left-hand side here, we have x squared minus 2x plus 1 equals x plus 11. Now I can subtract the x and subtract the 11. Was it x plus 11, right? Yeah, it was. So we have 0 on the right-hand side, and we have x squared minus 3x minus 10. Factoring this, you can use the AC method. This thing will factor down into x minus, minus 5 and x plus 2. Negative 5 times positive 2 is negative 10, and then negative 5 plus 2 is negative 3, so that's correct. And this gives us two answers, x equal to 5 and x equal to negative 2. Now, a very common theme in radical equations is that you will actually end up adding in an answer that's incorrect. And so you must check your answer. So you check your answer by plugging it back into the original problem. Don't plug it back into something that you've changed around. It could end up being correct and when it's not supposed to be. Plug it back into the original one. So for this top thing, I'm going to just plug in 5 and I think negative 2. Let me copy it down here. Yep. Okay. So let's plug in 5. So we get 5 and 5. This gives us 5 minus 5 plus 11 is 16 equals 1. The square root of 16 is 4. And 5 minus 4 does in fact equal 1. So that solution checks out. Let's try negative 2. Plug negative 2 into the equation. We have negative 2 minus negative 2 plus 11 is 9. And the square root of 9 is 3. Negative 2 minus 3 is negative 5, and negative 5 does not equal 1. So we must exclude the negative 2. The 5 is our only solution that is correct, so that's going to be our answer there. All right, sometimes with these, as you can see, we had one radical, so we had to do that. Sometimes with these radical problems, on the right-hand side here, we have two radicals. And the same process if you had 3 or 4 or 5 or however many you had. The idea is that you isolate a single radical first, then square it to get rid of it, or cube it, or fourth root it, whatever you need. And then you need to simplify the whole thing down and then get the next radical, because there's going to be the next radical there, and you need to get that by itself. So it's a multi-step problem. So the first thing I'm going to do here is I'm going to add the y minus 3 to the other side of the equation. That gives me the first radical, y plus 5, by itself, and then I can square it to get rid of the radical. That does mean that I have to square everything in the right-hand side, and I will have to FOIL that out. So it could be a little bit of work, but on the left-hand side, we just have y plus 5. On the right-hand side, we have, see, this is the same thing as 2 plus root y minus 3, and 2 plus root y minus 3. We can use the FOIL method there. That's going to give us 4. And then 2 times y square root of y plus 3, and the square root of y plus 3 plus 2. Those are like terms, so they can combine into 4 times the square root of y plus 3. And then finally, the square root of y plus 3, sorry, y minus 3 times the square root of y minus 3 is the square root of y minus 3 squared, which becomes y minus 3. The square root will actually cancel because it's multiplying by itself, and that is the square, so it cancels with the square root. Now you can see that we have a single radical equation, and we can solve this equation like we did with the previous one. Get the radical by itself and square it. So first off, I'm going to combine like terms. I have 4 and negative 3. That's just 1. Plus y plus 1. I can subtract y and subtract 1 from both sides. It cancels with the y's. All the y's cancel there. And now I have 5 minus 1 is 4 equals 4 root y minus 3. This one was really nice because now I can divide by 4, and that's a nice number to work with. 1 equals the square root of y minus 3. Now I can square it. And this one's nice to work with. I just get 1 equals y minus 3, so therefore y equals 4. I still need to check this because this answer could have been created from the process that we've been doing, and it could be wrong. So I'm going to take the original problem that I had and plug in 4 into it. Okay, 4 plus 5 is 9. 4 minus 3 is 1. The square root of 9 is 3, and the square root of 1 is 1. And 3 minus 1 does equal 2. So y equal to 4 is perfectly fine as an answer. So after we discussed radical equations, radical equations can be rewritten as the powers of a rational exponent, because a fraction in an exponent, the top part is a power and the bottom part is a square root or a cubed root or a fifth root, or whatever. So rational exponents in general is the idea of what happens if you have fractional powers and how do you solve these equations. Now we can solve these using properties of exponents, and kind of similar to what we just did with the radical equations. But there's an important thing to note, and that is that whenever you have an even power like we have here on top, so we have 2 on top, that's even, you must include a plus or minus. If it's odd, you don't have to worry about it, but you must include a plus or minus when you take care of this power. And that's because if we look at x squared equals 4, if you take a square root, you get x equal to 2. However, negative 2 also satisfies this. Negative 2 times negative 2, negative times negative is positive, and 2 times 2 is 4. So in fact, you also must include the negative result. And so that's the reason why you have to add a plus or minus when there's an even power. The same thing is true if I had x to the 4th equals 16. This implies that x equals plus or minus 2, because plus 2 to the power of 4 is 16, and minus 2 to the power of 4 is 16. This is not true for cubed powers or fifth root powers or seventh root. I keep saying seventh root. Seventh powers. Odd powers do not have this because negative 2 times negative 2 times negative 2, this equals negative 8. and 2 times 2 times 2 equals positive 8. So there's definitely a distinction between negatives and positives for odd powers. However, even powers, the evenness of the power cancels with the negative. That's the reason why you have to consider that. So with that in mind, let's solve this first equation. We need to take care of the power here and to get the x outside of the parentheses so we can solve for x. And the way we can do that is we can take this thing to the power of 3/2. And of course, you do both sides. And a power to a power multiplies the powers. So we have x plus 5 to the 2/3 times 3/2 equals 4 to the 3/2. I had an even power and I got rid of it, so I need to add a plus or minus in front of the answer. And 2 cancel with 2, 3 cancel with 3. The power just becomes 1, so I can drop the parentheses and just write x plus 5 equals plus or minus 4 to the 3/2. Now, what is 4 to the 3/2? Well, there's a couple ways you can do this, but the easier is probably taking the root first. 4 to the 3/2 is the same thing as saying the square root of 4 cubed. It's also the same thing as saying 4 cubed and the square root. This, the fractional power of 2 is the one that goes in front, and the 3 goes on top. The same thing with the other way. In general, this first method is more simple to solve because by taking the root first, you have smaller numbers which are easier to work with. And the square root of 4, well, that's just 2. 2 cubed is 8. So 4 to the 3/2 power is just 8. And at this point, you see we have two answers here. So how do we do that in the problem? Well, you can do that by splitting this thing up into two equations. The first one with the positive version and the second one with the negative version. Now we can solve each one individually. Of course, it's the same step. We get x equal to 3 and x equal to negative 13. Now, just like in the last one, we had a square root. Here we had a cube root actually in the original problem. We had a cube root here because there's a 3 in the denominator. We should check our answers just to make sure we didn't add in anything that's incorrect. So the original problem was, let's see, x plus 5 to the 2/3. And this equals 4. Now we can plug in our solution. So plug in 3 first. 3 plus 5 is 8 to the 2/3. 2/3 is the same thing as the cube root of 8 squared. The cube root of 8 is 2. And 2 squared equals 4. So that one checks out. Now let's try the next one. So let's try negative 13. Negative 13 plus 5, that is negative 8. And the cube root of negative 8 is negative 2. Negative 2 times negative 2 times negative 2 is negative 8. And negative 2 squared does in fact give us 4. So both of these answers are correct, and we're good to go there. Let's look at another type of fractional, or I should say rational equation. We're going to have 8x to the 5/3 power minus 24. And here you see we have an odd power with an odd power. The odd power is on top, so therefore we will not have to worry about a plus or minus version. So let's first get the x by itself. That way we can get rid of the power. This is like the same thing as getting the radical by itself in the previous set of equations. I'm going to divide by 8 here. That gives me x to the 5/3 equals 24 over 8 is 3. Now, let me write this a little bit bigger here. X to the 5/3, if I can write my 5s correctly. This is the same thing as to the power of 3/5 to both sides. That will cancel these powers and give us x equals 3 to the 3/5. In this case, the 5th root doesn't help us if we take it first. That's because there is no nice 5th root of 3. The 5th root of 3 is going to be some decimal number, probably 1 point something. It's just not going to be nice to work with. So instead, I'm going to take 3 cubed first because I can find that, and then take it to the 1/5 power, or in other words, the 5th root. 3 cubed is 27, and 1/5 power is the 5th root of 27. Again, there is no nice number for the 5th root of 27. It's going to be some decimal number, and it's not going to be easy to work with. So this is our answer. You can take this and plug it in back into the original equation right here, and you'll see that it'll give you a true statement. But that's how you handle rational equations. Sometimes equations can be changed to look like other equations that we know how to solve. So in this case, we're going to change these equations to quadratic equations and then convert back in the end. This is a very important, it's called the substitution rule in calculus. It's very important for that work. A lot of times quadratics or polynomials are easier to work with than these equations by themselves. In this case, we call this quadratic in form because I'm changing it to a quadratic. But you can do this with any polynomial equation that you want, as long as it satisfies the form, the correct form. And these do, because if I were to ignore the negatives here for this left-hand equation, this is a quadratic. So this can be changed to be quadratic in form, and I can do that by giving a different variable. I'm going to say y equals x to the -1. So x to the -1, which is right here, and then x to the -2, that's the same thing as saying x to the -1 squared. That's the same thing as x to the -2, and we can see an x to the -1 right there. So I can change this to y squared minus y minus 6 equals 0. And this is just a quadratic equation. So I can solve this by factoring. I can factor this down to y minus, let's see, y minus 3 and y plus 2. -3 plus 2 is -6, and -3 times positive 2 is -6. And -3 plus 2 is -1. And now I get y equal to 3 and y equal to -2 as answers. These are not the answers to our original equation, however. We changed the variable x to the -1 into y, so we need to make sure we change it back. And we can do that by just plugging it back in here. So we have y equals x to the -1. And x to the -1 equals -2. And the -1 power is just the reciprocal. So we have 1 over x equals 3 and 1 over x equals -2. To get this, to give us the answer here, because they're both a single fraction, I can just flip both sides of the fraction, giving us x equals 1/3 and x equals 1 over -2, or in other words, -1/2. It's important to note here that x cannot equal 0. If it did, you'd have a division by 0. But as you can see, our answers did not contain 0 in it, so we didn't have to worry about that. All right, for this next one, we have x to the 2/5 and x to the 1/5. This is again quadratic in form. I can just say y equals x to the 1/5. That means this first one becomes y squared. You can just check this. X to the 2/5 equals x to the 1/5 squared. And this is just y. So that's why it's y squared. X to the 1/5, that's just y, minus 6. This one factors down into x plus 3, y minus 2. And we get y equals -3 and y equals +2 there. Again, change it back. Y equals the 5th root of x. So the 5th root of x equals -3, and the 5th root of x equals 2. Now I can solve this by just taking the power of 5 on both sides. It's like if it's a square root, we take the square of both sides. That's the same idea. And what is the 5th root of -3? It is -243. And the 5th root of 2 is 32. And there are our two answers for that. So again, the first step is to change it to be a quadratic, and you do that by giving a clever substitution. And then you solve it in general, how you solve quadratic equations, factor and get the solutions, and then make sure you go back to the original variable. And if you don't do that, you're going to get incorrect answers. Like these are not the correct answers, as these are not the correct answers as well. As the last type of equation that we're going to look at, we have absolute value, and we discussed absolute value in a previous video of absolute value of numbers. And absolute value stands for a distance. On the number line, there are two directions that you can go to. Kind of like from the positive side and the negative side, two directions that you can have for distance. In the plane, there's a whole circle of directions that are the same distance, equidistance from a point. But in this case, we're thinking about a number line. So we should expect two answers here because, again, there's two directions you can come from. The absolute value, the way we can solve this is once we get the absolute value by itself, like we have in the left-hand equation here, we can split this up into two equations. The first equation is the positive, equals 11, and the second equation is the negative, equals -11. And now we have two linear equations. So get the variable by itself, and you'll have your answers. I'm going to add 3. Again, this is the same thing for both of them. We have 2x equals 14. X equals 7. And then on this side, we have 2x equals -8 divided by 2. And we have x equal to -4. In general, they will not be the same answer. They could be. It depends on what's on the inside here, the absolute value. But in general, they will not be the same answer, and they will not necessarily be one positive and one negative. So don't assume that that's always the case. You could have two positive answers, but they will typically be different numbers. Now, if we do not have the absolute value by itself, like we have in this right equation, we need to get it by itself. Just like we got the radical by itself and the rational exponent by itself, the same idea. I'm going to subtract 7 first. That gives us 4 root equals 3, and then divide by 4. I forgot the x here. That gets the absolute value by itself. Equals 3/4, and now we can split this up into two equations. 1 minus 3/4 x equals positive 3/4, and 1 minus 3/4 x equals negative 3/4. So we can solve this as we normally would. Subtract 1, negative 3/4 x equals 3/4 minus 1 is the same thing as 3/4 minus 4/4. It's going to be negative 1/4. And then negative 3/4 x. Again, we have 4/4 here. It's going to be negative 7/4. Now we can either divide by negative 3/4 or the same thing as multiplying by negative 4/3 to both sides. The same thing on this one times negative 4/3 times negative 4/3. The 4's cancel, the negatives cancel, and we get 1/3 for this first value of x. And the second one, the negatives cancel, the 4's cancel, and we get x equal to 7/3. And there's our two answers. They're both positive and they're both fractions. And so that's how you can solve absolute value. There should be one thing you always remember, and that is a distance can never be negative. Which means if you ended up with an absolute value, something like, let's say we had like 2x minus 5, I guess, I don't know, and this equals negative 3, you can immediately stop the problem because this has no solution. Distance can never be negative. It can equal 0. If it equals 0, you actually don't need to split it up. So for instance, if we had 2x minus 5 equals 0, this is the same thing as saying 2x minus 5 equals 0. There's only one solution. But if it's negative, there are no solutions. So make sure you do not continue with 2x minus 5 equals negative 3, and then 2x minus 5 equals positive 3. This will give you two answers that are incorrect. If you check them, they would not work out. So you could always check your answers to make sure, but it's kind of more important that you understand that a distance cannot be negative.